If you are viewing this strictly on YouTube, there is a lot of review, but you have the option to fast forward to parts that you don't want to view. If you're viewing this on Blackboard, then I've used some interactive video options to allow you to fast forward to the sections that you actually want to see, as opposed to the ones that are review and you maybe feel very confident in. So what is an array? Really, I think the best definition to go with is that it's simply just a collection of the same elements of the same data type. When would I want to use an array? And I think the best answer to that is if you want to save multiple records of the same data type. If you use the analogy of, say, road housing or town housing, you can see that's an array. It's the same data type, and in this example, it would be, let's say, the number of people that live in each house in each family. And because it's an array, or in this analogy, row housing, it has one street address, which is the same thing with an array. In this particular case, we've got unit addresses. So you have a street address and a unit address. And you'll note here that we start with 0, not 1. And that's to identify the first element of the array. If you look at this example, family size, I've got 4 elements. Even though the element starts with 0, there are clearly 4. 0, 1, 2, 3, 4. And we can go ahead and actually populate each one and say that within each unit or within each element, the first one has 6 family members, the third one 3, 4, and 5. So if we look at this from a syntax point of view, we can say that our array is called family size. Its type is integer because I don't have partial family members. I can populate my array through initialization, as I've done in the first line. But how do I actually programmatically put that into each of my elements? And the answer is that we use a for loop. You'll notice that in this array, the size is actually 4. It has a boundary of 4 elements inside this array. And as we cycle through the for loop, you'll see that you can only go to the very end of the boundary without getting an error. But if we look at the condition, that's perhaps the most important part of the entire array. This is the boundary for which the array length is defined. And we chose 4 because that's defined as the length or size of the actual array up above. Let's look at what happens when we start a for loop. And I should point out that whenever you have an array, you're almost always guaranteed to eventually see a for loop with it. That's how we traverse the array to begin with. So let's start at the beginning of this. We know we're starting off at element 0. And in the for loop, we're saying I equals 0. That means I is at element 0. And from there, we go through one single revolution and we're incrementing. So we've gone to 1 position and I can output the number 6. I'm at 6 and I need to go through again and I iterate through the for loop. And that puts number 3 into that element. And so on. I can go and populate with number 4. And again, I can go through and get to number 5 in the 4th element of the array. But what happens when I can't go beyond the specified boundary of my for loop? Well, that's what we're going to talk about today. We're going to talk about the subject of dynamic memory and dynamic memory allocation. I think it's fair to very quickly do a review of pointers. And what have we said pointers were? A pointer is a variable that holds an address as its value. And see here in a memory model, you've got the name, the type, its own address, but a pointer holds the address of another variable. That's not the address of itself, that's the address of another variable. We use the address of operator, and we also use the contents of asterisks. It's also known as the dereferencing operator. And one thing to note is always initialize your pointer to a value or a null. So if we look at this example, I've got an int num equals 25. It has its own address, its own name, its type, and a value. But then I want to use a pointer. So I call this one int ptr num, or pointer num equals null. I'm initializing it to null because I don't yet have a value for it. So this is what the pointer looks like in a memory model. But I want my pointer to actually point to my variable called num. And how I do that is I simply put the value of the address inside my pointer. And if you can see on my pointer, I've changed my pointer initialization from null to &num. That puts the address into the value of my pointer. Let's quickly look again at our int family size 4. What you see here is an array of int, or integers, 4 byte integers, and each of those carries the actual values that we are initializing. But there's only one address. The array only has one address. If you've seen in the last video, you'll realize that an array in fact is a pointer. Seen here in this slide, if I try to print out to the console what family size is, I actually output an address. And if I try to point to that array, it doesn't really work. I don't need the ampersand. All I need is the name of the array, and I can initialize that into the pointer. So when I try to print out pointer to the console, what I get is the same result as if I tried to print out family size. Yes, an array is the same thing as a pointer. It's vital that you understand that. Two things I want to get to in this video are C-style character strings and C++ strings. They are not the same. And I think now it's an appropriate time to head over to Visual Studio and have a look at C++ strings. And then we're going to come back and compare that to C-style character strings. What you can see here in my video called cpp strings.cpp is that I've got the name with the type string. And notice up here I'm using the #include string. There's no H. This comes from the C++ string library. All this program simply does is ask for string name. So enter your name, and then it takes the name and it outputs the name that I've typed in. So if I go ahead and run that, I'm going to show you the result. So I'm just going to type in my name, Tom. And everything worked fine. What happens if I want to type my entire name? Notice here when I type in Tom with a space M, see what happens? It cut off the space and M. And that's a big issue that we have to deal with when dealing with a string. What I want to do now is show you an example of how to actually get the entire string to output to the screen. In this program, there are several things that I do want to highlight. First off is I've kept the pound include string. This is the C++ string library. And notice what I've done is I've created a variable called greetString, and its data type is a string, and it's a lowercase string. But notice here it's inside a function. We'll get to that in another video. But I want to see out or print out to the console this line here. You can see on line 11, I'm asking for the user to have an input. And on line 12, I created another variable called string first line. What I want to draw your attention to is line 13, this get line. Get line is a library function from the string library. And what you're seeing is my cin inside as a parameter to the function, and whatever I type in is going to be initialized into the variable called first line. Same thing on second line from line 15 to 17. And line 19, what I'm going to simply do is start the beginning of concatenating my two lines. So if you see on line 20, I'm taking first line and I'm concatenating it with second line, and then I'm going to output the concatenated strings. On line 23, I'm going to make a copy of the concatenated string from line 21. That's because I eventually want to show you the length function that you can see on line 27. On line 27, my goal here is just to show you or print out to the console the length of all the characters in my two concatenated strings. So I'm going to go ahead and run that and show you the output. For the first line, I'm going to type C strings are different than C++ strings. And you can see the result here. And the important thing is here I was able to call that function, and you'll note that the number of characters within my two strings was 40. There are 40 characters within the two strings. Now, we've looked at C++ strings. Now it's time to go look at C-style character strings, because they're an important use of dynamic memory inside of C++. A char is another way to represent strings in C++. It actually came first with C. It's also known as a char star string. And C string is an array of chars, or it's an array of characters. And character arrays are terminated with the null terminating strings. Character arrays are terminated with the null character. And null terminated strings denotes end of a string. This is a very important thing. We're going to look at it in a little more detail as we continue. So let's look at a little sample of code here. What I've got is a const int max equals 80. And I've got a character array called string. And it's an array with a maximum size of 80. So when I enter data into a string, what I'm doing is actually entering characters into an array. So let's suppose that I type in the name Tom. This is what it looks like in memory. I have an array, and each character goes into each element of the array. So these are characters in the string. Each character occupies 1 byte of memory, and this is the terminating 0, or the null character, as a null character constant. This is the entire string itself. Notice the difference between the characters in the string and the actual string itself. And this is the unused part of the buffer. And here's the entire string buffer str. When the extraction operator displays the string, it displays characters until it encounters the null character. Let's look at a more practical example. Here we have a class named student. It's got an int student number and a char grade array of 14 characters long, and then one function, the set function. Let's take a deeper dive into the set function itself. If we look at the condition of our if statement, if my student number is greater than 0, then I'm going to perform an assignment of stu_num equals student num. But then I'm going to call this string copy underscore s. This is part of the C++ string library function. And what's key about this is the way the parameter list is set up. First, we have the destination that we want to copy into. The second parameter is the source that we are copying from. And then finally, we're copying the size minus the null terminator, which gives us the number 13, which is one less exactly than the size of our char grade array. Finally, if the condition of the if statement is not met, we go into the else. And in this case, we assign 0 to student number, and we assign the null terminator to the actual array. To look at our family size array again, what happens when we actually don't know ahead of time what the actual boundary of the array is? So for example, if you look here, I don't actually know how big this array is going to be because the users haven't actually typed it in yet. Nowhere on this array do I know what the limit is, because we're going to put that into something called dynamic memory. So for example, when you write an essay in Microsoft Word, you have no idea ahead of time how long the essay is going to actually be. Everything that you're typing into the text is dynamic. It's not hard-coded into your essay already. So that's what we're going to do with C++. We're going to use dynamic memory to input data into an application, but we don't know what the boundary of our array is ahead of time. So we need dynamic memory. The scope of a declaration is the portion of a program over which the identifier is visible. So we typically talk about two different types of scope, and the first one being global scope. And its declaration is visible to the entire program. And you can see here I've got int n in a global position above main. So the entire program can actually see that inside of main. The second one is block scope, a declaration in a code block and local to its block. Local variables are objects. So in this example, you can see I've put int I equals 6 inside of main. It's inside the code block. If you look at this particular example, I've got main, which is the larger of the two scopes. I haven't defined anything globally. I've put everything locally, but even within a local scope, you can see that I've got further scopes. So if we take a look inside of main, what's actually happening, you'll see that main's scope is starting here. In the first cout, I'm outputting 6. When a declaration goes out of scope, the program loses access to the variable or object. But we get into the for loop and we see the beginning of the first brace. And for that scope, life starts there. And then we get into the for loop itself. When the scope of that for loop truly begins, we can start to see the results of the output, which is 0, 1, 4, based on a calculation inside of the scope of the for loop. And as we get to the final bracket or brace, life of that for loop actually ends. The counter j declared within the for loop statement goes out of scope immediately after the closing brace. And as a result, we can output 6 again, which is the same 6 as we've output at the very top. We cannot refer to J after the closing brace. And as the compiler continues to process the code, when we get to the final brace within the main, life actually ends for the entire scope of main. When a variable or object goes out of scope, the space becomes available for a newly defined variable or object. That's a key takeaway. What I'd like to do is talk about two different types of memory within your computer. There's stack or static memory, which is a product of your RAM, and heap space. This is where we have dynamic memory. The user inputs new data during a program execution in runtime. Let's talk about static memory, which is the memory that the operating system allocates for the application at load time, which is called static memory. This includes the space allocated for program instructions or your source code, local variables, and local objects. The compiler determines the amount of static memory that each translation unit requires. The linker sets the amount of static memory that the entire application requires. This amount cannot be changed during execution. And dynamic memory, which is the memory that an application requests from the operating system during execution, is called dynamic memory. It's completely distinct from static memory. And the operating system reserves dynamic memory at runtime, and the application itself allocates and deallocates regions within the reserved memory. Something that's important to note is that if you do not deallocate, the memory becomes inaccessible and survives until the application ends. In terms of using dynamic memory, there are some things we should discuss before we go further. One is that all primitives are stored in the stack. All that was made without the new command is stored in the stack. Using the new keyword, we can now allocate memory on the heap. Deleting these objects can be done using the delete keyword. So for example, if I have a pointer I, I'm initializing with the keyword new. But when I want to deallocate it, I use delete I. A string pointer is deleted as a string as well. And then finally, an array using the new keyword also gets a delete. But notice with the deleting of the array, I'm using the square brackets. Dynamically allocated memory does not automatically go out of scope and does not become automatically available again until it is explicitly deallocated. So let's look at how this all happens. We've got static memory, and within that static memory, you've got your normal program instructions, and then we have some variables and objects. In this case, I've got a pointer with a char type, and I've got dynamic memory. So we use pointers in static memory pointing at dynamic memory. So when we start the IDE, we have our source code in the program instructions in static memory with our variables. We need a way to create new memory and hold on to it. To keep track, we store the address of each region allocated in a pointer variable from static memory. We must keep the pointer alive in scope as long as we need access to that region of dynamic memory. The lifetime of any dynamic variable or object ends when the pointer that holds its address goes out of scope. Therefore, it must be deallocated earlier. Let's look at another code example. In this case, we have the same code that we looked at earlier, which was our class student. And it's got two variables. One is an int, the other is a char array, and we've got a void set function. So here's the code. There's a lot of stuff to go through in this, but we'll go one by one. So right off the bat with point 1, I've got a null address. So I've created a pointer called software student, and it's of type student. So let's just pause for a minute and consider what that actually means. Typically what we've been doing thus far is using primitive variables. For example, an integer or a char or a double. But in this case, we're using the class, we are creating our own variable type. And in this case, it is a student. So with our point 1, we've got student as our data type. But also note that we're actually using that student as a pointer, which takes pointers to a whole new level. So I'm asking that you enter the number of students. We're using cn to get the number of students. And then the next thing we're doing is we have to allocate memory. And notice here, we are taking the pointer and we're using the keyword new student and number of students. After point 2, we immediately go into a for loop. And you'll note that within the for loop, the boundary, the limit of the for loop, is actually the number of students that we gave it when we typed it in at the very beginning. And as we use the for loop to cycle through that code, you'll see a number of things happening. And just at the bottom of the for loop's scope, you see software student i.set. We're actually calling the function from the class on the student software .set. And what that is the student number and the grade as parameters into that function. Once we get outside of the scope of the for loop, you see that we're now calling the delete keyword on the pointer. Once we use the delete keyword, now we are setting the actual pointer, software student, back to a null pointer. And finally, do not omit the square brackets after the delete. It goes hand in hand with the char grade array. I want to talk about a couple of phenomena that can happen with your memory. And the first one is a memory leak. This occurs if an application loses the address of dynamically allocated memory that has not deallocated. If the pointer goes out of scope before deallocation, or if the pointer changes its value before deallocation, this could result in a memory leak. And we might only become aware of a memory leak indirectly through progressively slow execution or incorrect results from what we expect as an output. Let's take some time and sequentially go through the steps in dynamic memory. So the first one being that step 1 is declare a variable for the for loop that will be used to populate the array elements. And in this case, int number of students. Step 2 is create a pointer to find the dynamic memory once input, and then assign it a null pointer. This is something that happens in your static memory. This must be kept alive as long as we need access to dynamic memory. So initially we're looking at student, software student equals null pointer as a pointer. When the pointer goes out of scope, the life of the dynamic memory dies with it. Step 3 is that we use the keyword new and number of students to allocate space in dynamic memory for an array. So this is basically pointer equals new type and then give it its size. In the earlier example, the size was number of students. And finally, in one line, it just simply looks like software student equals new student, number of students. And step 4, use the keyword delete and the square brackets to deallocate space in dynamic memory for an array. So at the very bottom, you're seeing just simply delete the square brackets software student. And then 5th, you have to assign the pointer the null pointer again. So software student equals null pointer. This is something you have to do in order to return back to that original state. And if you look at all the steps together, you've got step 1, declare a variable for the for loop, create a pointer, use the new keyword, use delete, and assign the pointer back to its null pointer again. So let's go look at some code. So as you can see in this project file, I'm calling it dynamic mem, and I've got 2 source files, which is main.cpp, which is open right here in the middle, and then I've got the header file, which is student.h, which is linked right here, and then open here, and then back to main, and I've got my CPP file for student, which is the actual definition file for my header file called student. So you can see here, this is the class student, and it's got 2 member variables, and it's got 1 function. And when I go to my student CPP, here I'm only addressing the actual implementation of my set function that you saw in the header file. And as you can see here, I've got 2 parameters that I'm passing into the function, the stu_num and a char pointer called g. So we've previously seen the code here in the .cpp. Nothing has changed there, but what I'd like to do is just simply go through and have a look at main and make sure everything is there. So right away, I've got my variable for step 1, which is my for loop. I'm declaring a pointer. I'm using new, and I'm going to iterate through this. And during my iteration inside the for loop, I'm actually going to call the set function. Once I go outside of the scope of the for loop, now I'm using my delete keyword, and I'm going to reset my pointer back to its original state, which was a null pointer. So let's go ahead and run this. So what I've got is enter the number of students. In this particular case, I'm just going to hit 2. 2. Student number 1, 2, 3. Grade 80. Now, because it's dynamic and I've input that I want to, it's asking me for a second option, student number 4, 5, 6. Enter, grade 90. And that's all. It's simple, it's complete, and we've used dynamic memory allocation because it's dynamic and we didn't know how many students were actually going to be input by the end user of this application. Note here that in this particular file, I'm not saving any of this data to a database anywhere, and I'm not printing out the results. That we're going to do in the future. But for now, the purpose of this video is just to demonstrate the use of dynamic memory through static and heap space, and really to allow for your users to have as much flexibility implementing the software as possible. Within this video, we really did cover a lot of ground, a lot of new topics, as well as some review of topics we've previously seen. My suggestion to you at this point is to go through and look at some of the code samples that I've provided or that I've worked through on here, and open up your IDE and practice and see if you can break it, see if you can do some debugging on this. This is something that does take some practice. There are other techniques or algorithms or functions that you can use to use dynamic memory. But for now, this is the best starting place when you want to create an application that has dynamic memory allocation. Thank you for your time, and I look forward to seeing you in the next video. Thank you.